Okay, imagine this. You have to build something perfectly square, maybe align it perfectly with the stars, but you don't have a single ruler, no protractor, no calculator. How would you even do that? Well, today we're going to uncover a system of mathematics that was born not from equations on a page, but from the raw, practical need to build. So here's how we're going to break it down. We'll start by asking how geometry even worked before equations existed. Then we'll see how ancient rituals were actually really complex math problems. From there, we'll get into the ingenious rules of the chord they used as a solution. And that leads to a huge question. How did they prove any of this without proofs? We'll look at their incredible engineering wisdom and finally wrap up with what this all tells us about where math even comes from. All right, let's dive in by traveling way back to a time before the kind of math we learn in school was even a thing. Long before we had X and Y axes on a graph, we had dirt, we had rope, and we had problems that needed solving. Geometry wasn't some abstract subject, nope. It was the essential toolkit for building your home, for measuring farmland, and, this is the surprising part, for conducting sacred rituals. So just to be clear, this is not a story about mystical powers or ancient secrets. It's a story about something much more interesting. How really sophisticated mathematical thinking just naturally emerges when people face specific, difficult challenges. It's a story of pure human ingenuity.
So, where did this ingenuity really get a chance to shine in ancient India? The answer is pretty cool, and a little unexpected. It came from the incredibly strict rules for religious rituals, which, when you look at them, were basically complex engineering projects.
Okay, and this is a really important distinction to make. The Greek or Euclidean geometry we all learned in school is all about abstract proofs. It's about asking why something is true. Vedic geometry was completely different. Think of it like a construction manual. It was a set of algorithms, clear step-by-step instructions for how to build something correctly every single time. And the biggest driver for all this innovation was the need to build these ritual fire altars, called chiti. Now, these were not simple pits in the ground. They were complicated structures with rules so strict that getting even one measurement wrong wasn't just a mistake. It meant the whole ritual was a failure. The stakes were high. And here's where the real puzzle comes in. How do you build an altar shaped like a circle, or even a complex falcon, that has the exact same area as the simple square one you started with? This wasn't some fun little brain teaser. It was a serious engineering problem that absolutely had to be solved. So how did they pull it off? Well, their solution was laid out in this brilliant series of instruction manuals, a collection of texts known as the Shulba Sutras. The name itself, Shulba Sutras, tells you everything. It literally means the rules of the chord. Forget laser levels or fancy equipment. Their #1 tool for precision measurement and construction was a simple, cleverly marked rope. And check this out. This is just brilliant. Look at how they found a perfect east-west line with just a stick and a rope. You pop a stick in the ground, draw a circle around it, you mark where the shadow touches the circle in the morning, and then again in the evening, connect those 2 points, and bam, you have a perfect alignment. It's a simple, repeatable, and incredibly accurate algorithm. Now, tucked away inside these practical, hands-on rulebooks, we find a description of an idea that should sound very, very familiar. It's not presented as some deep theory, but as a simple, powerful fact about how rectangles work. That's right, it's the Pythagorean theorem, centuries before Pythagoras. But the context is completely different. Here, it wasn't a theorem to be proven, it was a tool. It was a rule you used in the field to make sure every corner of your altar was a perfect 90-degree angle. It was about making things work. So, this brings up a huge question, right? If they weren't writing out formal proofs, how on earth did they know that their methods were actually correct? Well, it's fascinating because their system for validating knowledge has these amazing parallels to the modern scientific method. It wasn't about belief, it was about results. For them, verification wasn't a peer-reviewed paper. It was a successful construction. And consistency wasn't about reproducibility in a lab. It was about the method being so solid it could be repeated by different people over and over for generations. To put it simply, the proof was in the building. If the altar was built correctly, if all the pieces fit, if the area was preserved, then the geometry was considered valid. The system literally corrected itself through centuries of practice. Okay, but let's be intellectually honest for a second. This system wasn't perfect, and it had its limits, especially when it came up against some famously impossible problems. Take the legendary problem of squaring the circle, trying to make a square that has the exact same area as a circle. The Shulba Sutras didn't try to prove it. Instead, they gave a clear, step-by-step construction method, an algorithm, just like you see here, that produced a result that was so incredibly close it was more than good enough for any practical purpose. And this is the absolute key. Their goal was never abstract mathematical perfection. They weren't trying to solve some logic puzzle that, by the way, we now know is literally impossible. They were engineers who needed to build a functional altar that worked. For any builder or engineer, a good approximation that you can actually construct is infinitely more valuable than a perfect theory that you can't. This wasn't a failure to find the right answer. This was a triumph of engineering wisdom. So after all that, what's the big picture? What does this ancient system teach us about the nature of mathematics itself? Well, when you lay it all out like this, you see this incredible pattern. You could almost call it convergent evolution. Whether you're looking at an ancient system or a modern one, the path of knowledge is often the same. It starts with a real-world practical need. That need leads to rule-based methods or algorithms, and only way later does it evolve into abstract theory. The doing almost always comes first. And really, that's the ultimate takeaway here. This is such a powerful reminder to respect ancient knowledge for its raw ingenuity without trying to exaggerate it, and to appreciate modern science for its incredible rigor without being dismissive. They're both just chapters in the same amazing human story. It shows us that curiosity is really the bridge that connects these two worlds. And it leaves us with a pretty fascinating question. What other kinds of hidden mathematics are just waiting to be discovered? Not in ancient magic, but in their clever, practical methods.